Well, hello, welcome back. Hopefully by now you've studied some of the basics of energy and you know what we mean when we say kinetic energy or potential energy. And so in this problem, what I've decided to do is kind of put it all together. It's a bit of a ridiculous problem, but I think it demonstrates how we approach what I call a conservation of energy problem. And I've made it relatively simple, but we can make these more complex, although the process will still be the same. So it's really all about the process. I'm not going to show all the details and maybe show all the calculations. You should probably pause the video periodically just to make sure that the numbers that I get are numbers that you can also get. You're doing the calculation yourself. So let's take a look at what we have here. So I've created a problem with an inclined plane. It's a 5-meter long inclined plane. It's angled at 30 degrees, and we're going to imagine this to be frictionless. I'm using conservation of energy only because I can assume that all the mechanical energy that I have in this system, which in this case consists of a box, a spring, the ramp itself, and as always, although we don't usually state it, the Earth's gravitational field has to be an important part of our system. Well, that mechanical energy is going to remain constant. If I have things in a problem that are going to take away some of the mechanical energy, and those things are typically friction or air resistance, then I cannot assume conservation. So we'll get to those at a later time. So what I'm going to ask here is if I let go of this spring, so I've compressed this spring. Oh, and I didn't give that compression. So I'm going to write this as a delta x, and let's imagine we compress it a 0.5 meter. And so what I've done there is I've stored some energy by compressing the spring, and I'm going to let go of this, and I'm going to let this thing launch up the ramp. I'll just assume it stays in contact with the ramp, and then when it gets to the top, it's still going to be moving. So we want to find out how fast it's going to be moving. And then you can let your imagination run wild and figure out what could we do from there. We could turn this into a projectile problem, or we could imagine maybe we run into something else, or maybe there's a collision. So physics teachers can be pretty creative when they come to writing problems like that. But we'll start with just what is the speed at the top. And I think to organize my information, I'm going to use an energy table. And you may have seen me do this before. It's just a way of accounting for all the different forms of energy we have at the beginning of the situation, which is what the state is that I've drawn here. And all of our numbers will be in joules. And the final situation, or whatever you're asked about in a problem, in this case, up at the top, I'm not going to draw it there because it would get a little cluttered. And then I want to account for all the different forms of energy I could have anywhere in the problem. So let's start with, the most obvious one. I think you see a spring here. So I'm going to have some spring energy. And I'm also going to have some gravitational potential energy. I'm going to use abbreviations for this. U sub g. In my class, we use U for potential energy, and we use subscripts to show which form of potential energy we're referring to. So I actually could have called this one U sub s. That stands for a spring. I didn't want to write out the word gravitational, just a little longer. And then, of course, we're going to have some kinetic energy. And these are all the forms of energy that we deal with in mechanics that are considered mechanical energy. We will see some other forms of energy in a later part of my course. So then we'll have a column, or a row here rather, for the total amount of energy. So let's just start accounting for all the different forms of energy that we have. And I'm going to remind you as I do this how we calculate these forms of energy. In my class, it's an AP class, and so I have a reference sheet that I can refer to for all of these. Spring energy is calculated from 1/2 times the spring constant times the amount of squish, or in some problems it's a stretch, of the spring squared. So we start out with a K that's a 5,000. We've squished it 0.5 meters. We've done that calculation, and we get 625 joules of stored energy in the spring. Now, for gravitational potential energy, you have your choice of what you would like to measure from. As far as the height, this all is about the mass and the gravitational field that you're sitting in and the height that the object is. And that height has to be measured from some reference level. So I like to take the lowest point that I have in my problem, that I'm referring to as either initial or final, and I just call that one 0. It's pretty nice in this case because that also is the lowest point that we have, and so 0 is a convenient thing to put in for this initial. And kinetic energy, well, I haven't let go of it yet, so I also have no kinetic energy at the beginning. So you see I have 625 total joules of energy. And because I've assumed that it's going to be conserved, there's no what we call dissipative forces. Those are forces that turn mechanical energy into something like heat, typically. I have none of those, so I can assume 625 joules of energy at the end. Well, obviously my spring is not going to be squished anymore once it's up to the top, so I will have no spring energy. But I will certainly have some height, so I'll have some gravitational potential energy. So what do I need to calculate that? I need mg and then the height. This is the vertical height above the reference level. That's not this 5 meters, but that's this height right here. And I chose 30 degrees because I'm pretty good at taking the sine of 30. It's just 1/2. So I know that the height here is actually 2.5 meters. And so we can do that calculation and we'll get 196 joules of gravitational energy. So that leaves the rest of it to be in the form of kinetic. So how much is that? That would be about 429. My math is correct. We'll make a total of 625. So if we're asked for the speed, that's the magic number that we need, because kinetic energy is what determines, or will help us determine what the speed is. Really the other way around, the speed determines the kinetic energy. We're just kind of working in the other direction. So here's my equation for kinetic energy and how it relates to speed. Now we write v for velocity, but really we're just talking about the speed, because we don't need any direction information when we do this. We're not talking about vector quantities, just scalar. So I often write this in a more convenient form, 2 times the kinetic energy divided by the mass, and all of that square rooted. So when I plug in my 429 divided by my mass, I've marked 8 kilograms here for the mass, and then take a square root, I'm going to get a velocity up there of about 10.4 meters per second. So again, I haven't shown all the details here, and I would think if you're not trying to squeeze this into a 7 or 8 minute video, you would show all of that somewhere for you or your teacher to look at. But at least I've shown you the process. And like all things, when I show you a table, we could certainly write this in the form of an equation, just listing these 3 expressions together, all equal to, and then all of the final expressions added together, and then you can kind of do some algebra to solve for whatever you're looking for. I don't think it's as organized as the table, but some people prefer that. So I'll let you pick which way you like better. So I think that's going to do it for now. Hopefully that showed you how we use springs and gravity and kinetic energy all at the same kind of time to solve a problem, and you can tackle whatever problem you've got to face next. Good luck.